Welcome, everyone. Today, we are going to dive deep into a major transformation happening right now in artificial intelligence research. The paradigm shift from static large language model reasoning to what is known as agentic reasoning. For a long time, we have thought of reasoning as the core of intelligence, the ability to infer logically, solve problems, and make complex decisions. And large language models, or LLMs, have shown incredible, unprecedented leaps in these areas over the past few years. Think about how they can solve complex math problems or write intricate code. Techniques like chain of thought prompting have heavily boosted their performance by forcing the model to explicitly state its intermediate steps, essentially giving it computational space to think before answering. However, there is a fundamental catch. These successes are largely confined to closed-world domains. These are static environments where the question is fixed, and the model merely needs to generate an answer in one go. In the real, open-ended world, information changes rapidly, environments are incredibly dynamic, and true intelligence requires you to act, adapt, and learn over time. Conventional LMs are, at their core, passive sequence predictors. They are not built for continuous, grounded interaction with an evolving environment. This critical limitation brings us to our core topic today: agentic reasoning. What exactly happens when we reframe large language models, not just as passive text generators, but as autonomous reasoning agents? Instead of relying solely on its static internal parameters to generate text, an agentic system reasons through action. It can independently invoke external tools, explore alternative paths, update its internal memory, and seamlessly integrate feedback from its environment. We are essentially moving from a system that thinks and answers to a sophisticated system that plans, acts, perceives, and adapts. The foundational paper we are synthesizing today organizes agentic reasoning into three complementary layers. First, foundational agentic reasoning, which involves core, single-agent capabilities like planning, using tools, and searching for external information. Second, self-evolving agentic reasoning, where the agent improves through cumulative experience, utilizing feedback and memory to refine its own reasoning over time without full model retraining. And third, collective multi-agent reasoning, where we scale from isolated solvers to collaborative ecosystems of specialized agents working together. Across all these three layers of agentic reasoning, the research identifies two primary optimization modes. The first is in-context reasoning. This optimization focuses on scaling inference time compute. We orchestrate the agent dynamically using structured workflows and prompts, directing its reasoning process without ever changing the underlying model parameters. The second mode is post-training reasoning. This involves actually training the model weights to internalize these agentic strategies. This is typically achieved via reinforcement learning or supervised fine-tuning, embedding the ability to plan and act directly into the neural network architecture. To truly understand this profound shift in artificial intelligence, let us look at it through a more formal control-theoretic lens. We can mathematically model the environment the agent operates in as a partially observable Markov decision process, or POMDP. In a traditional LLM setup, the model policy takes an input and generates an output sequence. But in an agentic system, we introduce a critical new component, an internal reasoning variable. The policy of an agent is now factored into two distinct sequential parts. First, the internal thought or reasoning policy. The agent processes its history, observations, and internal memory to generate a hidden reasoning trace or a concrete plan of action. Second, the external action policy. Conditioned explicitly on that internal thought, the agent then commits to an action in the real world, like navigating a web page, calling an API, or returning a final answer to the user. This separation between thought and action is absolutely crucial. It highlights the think-then-act structure that defines agentic systems. We are no longer just mapping inputs to outputs. We are performing deep computation in a latent reasoning space before committing to an action space. This structural shift is precisely how artificial intelligence reasoning transitions from static prediction to interactive, highly adaptive intelligence. Now that we fundamentally understand what agentic reasoning is, let us examine how a single agent actually operates under the hood. Before we talk about how agents learn or how they work collaboratively in teams, we need to understand the bedrock capabilities of an individual agent. When a large language model becomes an autonomous problem solver, it moves from being a passive text generator to an entity that formulates strategic plans, explores diverse alternatives, and executes grounded operations in the real world. We call this foundational agentic reasoning. This foundational workflow is essentially an interconnected cycle of three core components: planning, search, which is often referred to as agentic RAG, and tool use. Let us break each of these down in detail. The first and arguably most critical step is planning. It is not enough for an intelligent agent to just know facts. It must figure out how to practically achieve a given goal over multiple steps. This involves decomposing a highly complex abstract goal into a sequence of tractable, actionable subtasks. In the early days of LLMs, we saw simple, linear reasoning, like standard chain of thought. But true agentic planning is much more robust and nonlinear. The research categorizes two main paradigms for agentic planning. The first paradigm is in-context search. This is where the model uses its context window to iteratively explore different possibilities, essentially searching through a vast thought space. The React framework is a classic and highly influential example of this. The agent continuously interleaves generic thoughts, concrete actions, and environmental observations to guide its progression toward a goal. Another powerful example is Tree of Thoughts, where the model explores multiple divergent reasoning paths simultaneously, structured like a decision tree. It evaluates nodes, backtracks when necessary, and explicitly decides which path is most promising to pursue. The second major paradigm is optimization-based planning. Here, the model learns to plan through training techniques like deep reinforcement learning. It is not merely prompting the model to think step by step at inference time. The model's actual neural weights are updated based on the ultimate success or failure of its generated plans. This internalizes the planning capability, making the agent inherently better and vastly more efficient at long horizon tasks over time. Our second core component in foundational agentic reasoning is search. We are all likely familiar with retrieval augmented generation, commonly known as RAG. Traditional RAG is essentially a one-shot process. A user asks a question, the system blindly retrieves a few top documents based on vector similarity, and the LLM summarizes those documents. Agentic RAG, however, fundamentally turns retrieval into a continuous, decision-driven process. The agent actively decides when it genuinely needs more information, exactly what specific query to search for next, and whether the retrieved evidence actually answers the core question. It can rewrite and refine its queries if initial results are poor, aggregate and combine information from multiple disparate sources, and independently decide when to stop searching because it has gathered sufficient evidence. Some advanced systems even perform complex multimodal search, seamlessly combining text retrieval with inspecting visual documents, images, or video representations to synthesize a comprehensive, grounded answer. Finally, an agent needs to act on its formulated plan and retrieved context. This is where the third capability, tool use, comes into play. An agent without tools is like a highly intelligent brain trapped in a jar. It can think, but it cannot affect the world. Tool use connects the agent's internal reasoning loop to external functional systems. This could mean generating and executing a block of Python code to precisely solve a complex math equation, querying a massive SQL database for real-time analytics, or even autonomously controlling a web browser to navigate the internet. What makes this tool use specifically agentic is the degree of autonomy. The agent parses its environment, autonomously decides which specific API to call from a massive library, formats the complex JSON arguments required, and critically, interprets the raw result. If a tool fails, say an API returns a 400 bad request error or the generated Python code throws a syntax exception, an agentic system does not simply crash and give up. Instead, it uses that exact error message as highly informative feedback, reflects on its mistake, revises its code or arguments, and tries again. This continuous, resilient loop of execution and verification is exactly what transforms abstract theoretical reasoning into concrete, grounded action in the real world. We have now talked extensively about how a single agent plans, searches, and uses tools. But an important question remains. What happens when that intelligent agent invariably makes a mistake? Or what if it faces the exact same difficult problem tomorrow? In traditional AI systems, if a model fails to solve a problem today, it is guaranteed to fail in the exact same way tomorrow, unless a human software engineer manually steps in to retrain its weights or rewrite its prompt engineering code. But agentic reasoning introduces a profound and powerful new concept to solve this: self-evolution. Self-evolving agents possess the remarkable capacity to actively improve their own reasoning processes directly through their own interaction experience. They achieve this continuous improvement by leveraging two fundamental mechanisms: feedback and memory. When an agent fails executing a task, it doesn't just halt execution. It receives an evaluative signal, which is feedback, indicating that something went wrong. And crucially, it has a persistent computational substrate, which is memory, to explicitly store that interaction, analyze and figure out exactly why it failed, and adapt its future approach so it succeeds the next time. This is what researchers call continual adaptation, and it serves as the foundation for true lifelong reasoning in AI systems. This evolution happens fundamentally on two completely different timescales. First, we have what is known as intra-test time evolution. You can think of this as learning while solving. The agent adapts dynamically during the actual execution of a single task. For example, if an agent tries to parse a specific web page to find a price, but the HTML format is entirely different than it expected, it uses its internal reflection capability to correct the error on the fly. It will autonomously devise and try a different parsing strategy before ultimately returning an answer to the end user. Second, we have intertest time evolution. This is learning across tasks, representing long-term growth. If the agent discovers and confirms a highly successful new heuristic or problem-solving strategy today, it explicitly stores that finding in its persistent long-term memory. A week or a month from now, when faced with a structurally similar problem, it rapidly recalls that heuristic from memory and leverages it to solve the new problem faster, more efficiently, and more accurately. In this way, the agent's capability fundamentally persists and snowballs across thousands of different episodes. Let us look a little closer at the concept of feedback in self-evolving agents. Where exactly does this critical evaluative signal come from? Sometimes, the feedback is purely external and explicit. A web API returns a standard HTTP 404 error, a Python execution script throws an obvious syntax error trace, or the visual environment, like a rendered web page in a browser, visibly changes in response to an action. But highly capable agents can also generate sophisticated internal feedback. Through self-critique mechanisms, such as the widely used Reflexion framework, the agent essentially acts as its own harsh judge. It autonomously reviews its own historical reasoning trace, actively identifies logical leaps or hallucinatory assumptions, and generates a concrete set of textual guidelines to heavily condition its subsequent attempts on the problem. This adaptation can take several forms. It can be verbal, where the agent simply updates its internal textual instructions and prompts. It can be procedural, where the agent actually synthesizes brand new, reusable code-based tools and saves them into an executable skill library for future use. Or at the absolute bleeding edge of current research, it can be structural, where the agent autonomously rewrites its own underlying source code or prompts to discover fundamentally better reasoning algorithms. However, absolutely none of this self-evolution works without the second mechanism: memory. Memory is how an agent accumulates vital context over time. In agentic research, we break this down into three distinct types of memory architectures. First, episodic memory. This stores the highly specific, step-by-step historical logs of all past interactions and trajectories. Second, semantic memory. This extracts and stores generalized abstract facts, heuristics, and concepts logically derived from those raw episodes. Third, procedural memory. This stores the refined executable skill sets or complex tool use access patterns. Crucially, memory is not just a static relational database. An advanced agent has to actively manage it. It must intelligently decide what specific information is actually worth writing to persistent memory, how to accurately retrieve the most relevant past experiences, when faced with a novel problem using vector embeddings, and how to periodically update, summarize, or heavily compress that memory so the agent's limited context window does not simply get overwhelmed with useless or redundant historical information. We have seen how a single, isolated agent plans, uses tools, and evolves its capabilities. Now, let us turn our attention to Segment 4, Collective Multi-Agent Reasoning. What happens when a given task is simply too complex, too broad in scope, or requires too many highly specialized, disparate skills for any single agent model to handle effectively? The answer is that we scale up. We move from relying on an isolated, monolithic problem solver to engineering a collaborative, distributed ecosystem. This is not just about instantiating multiple copies of the exact same LLM. It is fundamentally about role differentiation, specialized prompts, and the strategic division of labor. In a multi-agent system, frequently abbreviated as MAS, independent agents assume entirely complementary roles, much like highly trained humans do in a professional corporate organization. This architectural design distributes the immense cognitive load and allows individual agents to deeply specialize in specific subtasks, preventing context dilution. Let us look at the formal taxonomy of these specialized roles. First, there are generic roles that universally appear in almost any complex multi-agent system architecture. For example, the leader or coordinator agent. This agent maintains high-level structural coherence, actively breaks down the main objective into sub-goals, and delegates them. Then there is the worker or executor agent, which acts as the operational backbone, meticulously writing code, executing commands, or using specialized APIs. Crucially, we have the critic or evaluator agent, which acts as an adversarial quality assurance mechanism, rigorously verifying hypotheses or judging the outputs of the worker agents for flaws. We also see specialized memory keeper agents curating long-term vector knowledge and communication facilitator agents governing exactly how agents are allowed to talk to each other to prevent endless loops or communication bottlenecks. But what is truly fascinating about current multi-agent research is how these generic roles seamlessly map onto powerful domain-specific roles. For instance, in the domain of software engineering, en masse might directly mirror a real-world enterprise development lifecycle. You deploy architect agents to design the system, developer agents to implement the logic, code reviewer agents to enforce security standards, and release agents to handle deployment. In finance, you might structure a system with analyst agents constantly extracting unstructured market signals, paired with risk manager agents relentlessly running portfolio stress tests, overseen by compliance agents, ensuring strict regulatory adherence. And in modern healthcare research applications, a rapid triage agent assesses cases and routes them to specialized vision agents for radiology, before a lead physician agent meticulously synthesizes the disparate data into a holistic final diagnosis. So how do these highly specialized agents actually collaborate? How exactly do they divide the labor in practice? We categorize this interaction into two main dimensions. The first dimension is in-context collaboration. This type of collaboration happens dynamically at inference time without retraining the underlying neural network models. Some enterprise systems use manually crafted pipelines. These are rigid, predefined organizational hierarchies where the execution order and communication channels are strictly fixed by human developers. While this approach is highly stable and predictable, it is not very adaptable to dynamic edge case problems. Conversely, more advanced systems utilize LLM-driven pipelines. Here, a central orchestrator model dynamically routes subgoals to specific specialists entirely based on an active understanding of the context of the query. Sometimes, this dynamic routing is even augmented with a sophisticated theory of mind, allowing routing agents to actually probabilistically reason about the hidden beliefs, capabilities, and intentions of other agents to collaborate much more effectively. Then there is the second dimension, post-training collaboration. This is where we optimize the multi-agent system's fundamental structure through algorithmic learning. Instead of relying on human engineers, we might use evolutionary algorithms to autonomously search for the single best communication graph or network topology for a specific class of enterprise tasks. Or, we might use deep multi-agent reinforcement learning to explicitly train a lightweight router agent to become statistically better at selecting the optimal specialist for a given problem over millions of simulated iterations. Finally, just as a single agent can evolve, an entire multi-agent system can co-evolve. This multi-agent evolution specifically aims to rapidly improve the collective, synergistic performance of the entire group. To achieve this complex feat, the system requires an incredibly robust approach to shared memory. Engineers must decide, does the system use a strict hierarchical memory architecture to extract high-level global insights, or a heterogeneous design where each individual agent is forced to keep private, hyper-specialized local memories? Is the collective memory heavily centralized and aggressively verified for factual accuracy before writing, or is it distributed and freely shared among the open agent pool to maximize creativity? Training modern multi-agent systems to organically evolve their shared memory and dynamic coordination strategies, essentially shifting from a static, hard-coded hierarchy to a rapidly self-improving, autonomous organization, is arguably one of the most exciting and profound frontiers currently being explored in agentic AI research. Welcome to the final segment of our comprehensive lecture. We have analytically built our understanding of agents up from foundational single-agent skills through the mechanisms of self-evolution and into complex multi-agent collaborative ecosystems. Now, let us examine where this immense academic theoretical power is actually being applied in the real world today. Agentic reasoning is definitively no longer just theoretical lab research. Because these autonomous agents can strategically plan, execute comprehensive searches, expertly use software tools, and coordinate in teams, they are rapidly unlocking entirely new, highly complex commercial domains. In the realm of mathematical exploration and vibe coding, agents are not just passively solving known homework equations. They are actively exploring novel, unmapped geometries, independently identifying and rigorously proving new theorems, and functioning as fully autonomous, senior-level software engineers capable of navigating massive legacy corporate codebases to locate and fix obscure bugs. In the critical field of scientific discovery, we are witnessing the deployment of fully autonomous AI scientists. These agentic systems can independently read and pull data from millions of dense literature papers, generate novel, chemically viable hypotheses, seamlessly use incredibly complex computational chemistry modeling tools to rapidly evaluate and filter theoretical molecules, and even simulate rigorous multi-agent peer review on their own generated findings before presenting them to human scientists. In embodied robotics, agentic frameworks are fundamentally translating high-level, unstructured textual instructions from humans into precise, low-level physical motor actions within environments that suffer from severe partial observability, such as autonomously navigating a chaotic, unstructured 3D home environment to find a specific object. And in the high-stakes domain of healthcare and medicine, sophisticated multi-agent systems are increasingly acting as robust diagnostic ensembles. Instead of relying on a single fallible model, you have an ultra-fast triage agent rapidly mathematically sorting patient symptoms, followed by specialized oncology or cardiology agents debating the nuances of the diagnosis based on the absolute latest real-time medical literature, capped off by a lead physician agent that safely synthesizes the disparate, highly specialized data streams into one finalized, holistic recommendation for the human doctor. However, with all this immense, unprecedented capability comes a huge, immediate problem for the research community. How do we actually rigorously evaluate these agentic systems? Standard, static multiple-choice benchmark tests are entirely insufficient for autonomous systems that fluidly interact with complex, unscripted world environments. The foundational research paper divides modern agentic benchmarks into two distinct critical types. First, mechanism-centric benchmarks. These strict tests evaluate highly specific algorithmic primitives in total isolation. For instance, exactly how reliably can the agent formulate the JSON payload to use a single complex API tool? Precisely how well can it retain a critical piece of information in its long episodic memory over a sprawling 50-turn conversation? Can multiple adversarial agents successfully and fairly negotiate the allocation of a limited resource in an isolated, game-theoretic environment? Second, we require application-centric benchmarks. These broadly evaluate holistic, end-to-end task performance in chaotic, highly realistic simulated environments. For example, the OS World benchmark strictly measures if an agent can autonomously use a virtual computer desktop, clicking buttons and typing text across multiple separate applications, just like a human worker. WebArena rigorously tests an agent's ability to navigate massive, highly realistic commercial websites to successfully make complex flight or hotel bookings. These end-to-end simulations are vital because they test the entire fragile pipeline simultaneously: visual perception, long-term planning, grounded action execution, and multi-agent coordination. As we look beyond the horizon to the future, the rapid shift to agentic reasoning has exposed several massive, unsolved open problems that require urgent focus. Current agents still generally solve fixed, identical tasks. The immediate next frontier is true user-centric personalization, agents that dynamically adapt to you, deeply learning your specific workflow preferences and adjusting their behavior smoothly over years of long-term interactions. Furthermore, there is the fundamental mathematical challenge of long-horizon credit assignment. If an autonomous coding agent takes 10,000 distinct file editing actions to build a massive app and it finally fails compilation at step 9,999, how does the reinforcement learning algorithm possibly know which specific early design decision caused the ultimate catastrophic failure? Optimizing extremely long-horizon tasks is mathematically grueling. Additionally, to plan reliably in the physical world, agents desperately need an internal predictive world model to simulate physics and causality into the future before actually committing to acting. Training these world models efficiently alongside the agent is a critical active area of deep learning research. Finally, governance and safety. When you give an AI model persistent memory, multi-agent autonomy, and unlimited access to real-world software tools and APIs, the potential safety risks multiply exponentially compared to a chatbot. We urgently need robust mathematical governance frameworks that do not just align the base language model, but successfully align the holistic behavior of the entire complex agent ecosystem, interacting flawlessly with real-world infrastructure. Agentic reasoning is profoundly accelerating the evolution of AI. It is moving artificial intelligence permanently from a passive paradigm of merely thinking to a highly active, autonomous paradigm of doing. And the incredible reality is, we are just at the very beginning of this journey.